Hi everyone, welcome to another episode of the Data Standard Audio Experience. Today I'm with Cody Allen, a research engineer at Solar Turbines, and today we're going to be speaking more about network optimization. So welcome to the show, Cody. I'm excited to speak with you and learn more about your journey.
Thanks, Catherine. Appreciate being asked to come on the show.
Yeah, definitely. We're so excited to have you and just learn more about everything that you're working on right now. Go ahead and introduce yourself. Tell us how you kind of landed your role at Solar Turbines.
Sure. So just a little background on me. I hold a bachelor's degree in finance from Northern Arizona University, a master's degree in applied mathematics from San Diego State University, and then a PhD in control and optimization theory from UC San Diego, which I think you're an alum from. Go UCSD. And so I landed in solar originally from an internship during my master's program for applied mathematics. And so I got a summer internship there, and we worked on some time series analysis of some data signals that were coming from some industrial machines. And at the end of the time for the internship, they made me a really sweet offer that included paying for the PhD over at UCSD. And so I said, I happily accepted, and it's the rest is history.
Yeah, and that's so exciting just to have everything just all aligned for you and the path is just there for you. So that's great.
Yeah, it's very good.
Yeah. And so today we're going to be talking more about network optimization, and that's just the big topic of today. And can you just share with the audience what network optimization is and maybe how you've had to use it and deal with it at your company?
Sure. Yeah. So let me start with a bit of a mathematical description, and then I'll give some examples that I think will really elucidate what it is. So basically, there's a subdomain in mathematics called graph theory. In graph theory, you're going to have objects called nodes and edges, and you can think of, if you had a bunch of dots on a piece of paper and you started connecting them, the dots are your nodes, the edges are the connections, the lines between all of those dots. And then when you get into the specifics of networks, now, especially with network optimization, then you're going to have, what are called supply and terminus nodes. And so those will be where some sort of a flow through the network starts on the supply and then ends on the terminus. And from there, you'll have a capacity, usually a maximum capacity for any of the edges. So that's the maximum flow that edge, which is connected between two nodes, can handle. And then there will be some flow, which is a variable on, what the actual flow is between usually 0 and whatever that capacity value is. And so network optimization is the goal of typically maximizing the flow across the network, given some constraints on the network to be able to, have that maximum flow. And so a few examples would be transportation. So you think of streetlights and urban planning. You want to maximize the flow through your main roads, and, some of the constraints are you have a minimum flow maybe on some of your cross streets, right? Google Maps routing. So when Google Maps routes you through the most efficient route, they want you to flow through with a minimized time, right? And then, so electricity, as power stations produce electricity, you want to have the right flow to meet all of the power demands at, all the residences and all the commercial buildings. Communications is a good one. Think of data centers. You want to have all of your information packets flowing through your various servers in a way that's most effective, and your bandwidth limited on some of those different flows. That would be kind of like the capacity is the bandwidth, the maximum bandwidth. And then the last one that I'll talk a lot more about today is for gas pipelines. And so you think of natural gas, and we've probably heard, or maybe some of the viewers have heard about the natural gas incident or the power incident in Texas a few weeks ago. And so, big gas pipelines are there that are trying to distribute flows of natural gas to all of the end consumers. And so trying to optimize that and maximize that is a big goal of that area in network optimization.
Yeah, and let's talk more about that actually, since that's one of the more recent events that happened. Can you talk more about that project and how network optimization was really crucial for the data for dealing with the whole Texas issues that were going on?
Sure, yeah. So, with what happened in Texas, at least for the natural gas side, a lot of pipes froze. And so What that basically can be represented mathematically as is like all of a sudden that edge has a zero capacity because you can't flow any gas through there. And so with the tools that were in place, full disclosure, I don't work for the Texas gas distribution group, and so I don't know exactly what they were doing, but I imagine if in their network optimization models, what they were having to go and do is take the data coming off of the sensors in real time, probably of you start to see these ground temperatures that are sub-zero. And so usually natural gas pipelines are actually buried. And so the ground temperature has a big impact on what the temperature inside the pipe for the gas is. And so as that freezes and it either really slows the flow or stops it, that reduces your capacity. And so now all of a sudden the optimization model needs to know that so that it doesn't accidentally send a flow through a pipe that is really physically not available to flow through. And so, it's the idea is you've got to take this real-time data from all of these IoT sensors that you have on various parts of the pipeline, usually temperatures and pressures, and use that data to immediately update the model and some of your coefficients and some of your constraints. And then at that point, you rerun the simulation and then the optimization to see, does the answer change?
Yeah, no, that sounds awesome. And with all of this network optimization, of course, there's a lot of math involved. What are the biggest challenges that you've kind of faced using network optimization?
Sure. So great question. The typical network optimization problems fall into a subdomain of math called, mathematical programming. And then further, most of them are typically what are called linear programs. And so linear programs have, a linear cost or objective, and then also linear constraints. And so this program or this type of mathematical program is very well studied. There were some major results back in, I think, the 80s. Danzig came out with this algorithm that basically, I think, is still the crux of most of the algorithms that exist out there today. There's some really beautiful theorems out there that say, hey, look, in this particular case, we can guarantee a global optimum of your solution. And that's fantastic. For our particular problem, the physics is such that we don't have a linear program. We have a linear objective function, but we have quadratic constraints. And those quadratic constraints are something called non-convex. And so basically, in a nutshell, what that does is it nullifies that beautiful theorem and says, hey, you don't get to use that one because it doesn't apply. And then there are some other guarantees about the optimality of solutions, meaning that like you found the solution, right? You can't find any more optimized solution than the one that was found. Well, we lose that guarantee as well. And that's because of the structure of the mathematical equations that represent the physical elements out there. And so that's when you lose that, now, you have to do what are called heuristics in trying to solve the problem. And so I would say that's probably the biggest technical hurdle that we run into.
Yeah, definitely. And thank you so much for sharing, just because a lot of people, I'm sure, are facing similar issues at other companies too. And it's just important to speak about them and just maybe figure out a way together to figure it out. But
Sure.
definitely. And we know that just technology in general is always going to be advancing in the future. Things are always changing. Within the next decade, the problems that we have now will probably already be solved, but there's going to be a new set of problems that come in. And so, how do you kind of see the future of network optimization changing in the future?
Yeah, so it's an interesting question. I think, I'd like to go at it two separate ways. First, I think, as the world marches towards being more efficient in whatever metric you want to use for efficiency, mathematical optimization is the key to be able to measure and optimize that efficiency, right? And it's, going back to the data standard, as we take on more and more real world problems, you have to have data to inform the models. And so without that, your model is just a guess of what's actually going on, and then you optimize that guess. Well, great, you have an optimized guess, but that doesn't necessarily mean it's an accurate solution, right? And so it's that real world data, whether it be, ad clicks on Google or IoT machines over here with temperatures and pressures and humidities and whatever, data is crucial. So in the future, I think that what we're going to see is a lot more IoT data coming online, a lot more just like not personal data, but I'll say social behavior data. We're already seeing a ton of this, with Google, with Facebook, even Netflix, and some of the other bigger tech companies that are just, they have massive data lakes, and presumably they're using all of that data, but it's so massive that maybe they're not. Maybe there's some that's just archived and waiting for, as they grow, to go back and look at it. But I know in our industry, the more data we get, the more we can build better physics-based models or hybrid models that are physics-based but are informed by machine learning. And so I think there's going to be a lot more of that to come. The other thing is, in the future, I think the application, so that's kind of more on like the method side. That's what I think, that's where I think we're going. But on the application side, I think we can talk a lot about that too. And so, it's not super hard to imagine a few hundred years from now, maybe the network optimization problem that we want to solve is, which planetary systems should I visit on my way to some exoplanet where we have a colony of humans, right? And perhaps there are, various resources at these different planetary systems that we can use on our way there. Think of it as interstellar refueling. I don't know. We could, I'm not sure what it would be, but there are definitely going to be various problems that show up, especially as we push for efficiency of solutions. Many of those can be put into the framework of optimization, but even further into network optimization is my thought. And so I think, it's a good time to be a mathematician. It's a good time to be a data scientist. The world's opening up, and with the computational power out there, I think that this is just going to continue to grow.
Yeah, definitely. And on top of that, it's also a constant need from other companies to hire more people that have these skill sets. I know a lot of universities are trying to open up to teach the next generation more about just data science in general to get them into the field. So that's awesome. And outside of just work and all of the stuff that you're doing right now, what are you doing just to pass the time? Do you have any hobbies or interests that you're doing on the side just to pass some time?
Yeah. So I'll talk about two things. I have a website that I'm using some optimization theory for, to look at some financial optimization. And so basically, there's a pretty good theory out there called portfolio optimization. But it turns out that the math problem, when you step away from the data source, is extremely similar to the math problems that we're solving. And so I'm in the process of trying to get that up and running, to get it out there and see, if people would be interested. And then the other, I'd say, main hobby is, so I finally got my garage cleared out. And so now I'm trying to build out a workspace where I can do some experiments. And what I would like to do is I would like to actually perform some interesting data experiments with like a data acquisition system, but videotape them too. And so, you could imagine like a video of the experiment running, but then inlaid, you'd have all of your sensor arrays showing all of the values as they go. And so something that I found, so in the publications that I have, one of the big issues I've found, especially for the IoT data, is that if it's a company sponsored paper or presentation, they're reticent to release the actual data. And so, UC Irvine has a nice collection of data that spans all over the place, but their IoT data is a pretty small portion of that. And so there seems to be this dearth of IoT data for specific problems. And so like getting to the gas flow problem, it's not too difficult to set up an air compressor with a bunch of PVC pipes that have a bunch of valves and then various sensors throughout, and just play with it, turn the knobs and see what happens and record that data. And, one of the things I would like to do is be able to create that and then show, hey, all of this work that's going on, you can replicate this in your backyard if you want to. I mean, if you like this stuff, you can at least. And like really show, okay, let's bring the data, let's bring the actual application, and then let's show how we actually could model that on a really small scale. And so I'm in the early stages of trying to plan that out and negotiate with my wife for how much of the backyard I can take.
Yeah, that sounds super fun, the things that you're doing right now. But yeah, that's awesome. And I hope it all goes well, definitely.
Yeah, thank you.
Yeah. And thank you so much for being on the show, Cody. It was such a pleasure to have you today. Where can everybody find you online to connect with you?
Yeah. Thank you for having me. It was a pleasure to talk to you about, data and where it fits in society and network optimization. That was wonderful. Online, the only real online source that I check is LinkedIn. And so, if anybody wants to get into contact, drop me a message on LinkedIn or, just ping me in any way. That's the only social media I currently have.
Yeah, that sounds great. And to our audience, for more information on the data standard, you can find us at www.datastandard.io, as well as our LinkedIn and YouTube channel. And thank you so much, Cody, once again for joining us. Such a pleasure to have you, and I hope to speak to you again soon.
Great. Thanks so much, Catherine. It's great to be here.